Alright, time for another draft. Physics.com, debatephysics.com also, but can't get any of these physicist types to debate any subjects. Can't get them to talk about it, can't get them to interact with anybody who dissents regarding what they're saying. It's all pop culture run crap, majority think, group think, whatever you want to call it. And it's all very disappointing that you really can't challenge science and get some sort of answer. Now, it would be nice even if they had some sort of paid service. It used to be that they would do things for high school kids, like you pay them and you get some tutoring. But you should be able to pay them to actually respond to points made. So it would be nice if I pay him $100 and he answers a one-paragraph question. But now there's nothing reasonable like that, unfortunately. So it's just all very tragic. So anyway, this is a AlphaPhoenix video. I originally saw this guy, said, okay, this is interesting. He's kind of quirky and weird, kind of a nerd, whatever. So, but he was sort of interesting. But then he starts doing these videos where he starts making claims about, physics that are just, frankly, silly. But he did prove some good stuff. The speed of, energy through a steel rod, demonstrating that, the speed of sound in the steel is how fast the motion actually moves through the object. So you hit it at one end, and it has to move, the hit has to move at the speed of sound through the steel. It doesn't go some other speed. Then he proved basically that yes, the speed of light, inside of electrical systems isn't quite the speed of light. The electrons aren't being pushed exactly at that speed. It's like 70 or 80%, not, what people think, that it's as fast. So another good example, but that was part of the whole Veritasium silly crap about induction being where the action is, and induction is just a symptom of moving electrons. You move electrons in atoms, yes, they create a magnetic field that moves, and that's just not a big surprise that that's induction, but that doesn't have anything to do with the fact that you are moving electrons. They're the real thing you're moving. They're the real thing that has momentum. Yes, and so anyway, so yeah, some videos I could like, some videos I hate. I've just over time gotten to the point where I hate them. Yeah, so Bream Hassenfelder, same kind of thing. Originally, okay, seemed like a real person, and then they just become show producers, and you just lose all interest. So this is a really silly video where he's trying to rationalize Einstein's relativity. And so it's just like Veritasium. So he's just following along with these other idiots who have made these videos kind of trying to argue that we're moving up instead of gravity pushing things down, that somehow we're going that way and the whole universe isn't obeying properly, and so somehow we think we're falling when no, we're going up and the universe is going down, some kind of crap like that. I mean, it's just so fucking stupid. I mean, it's just silly. It's shit, frankly. It's just shitty science. All right, anyway. So, but it's my favorite subject now, gravity, because now that I know how gravity actually works and that you're actually being pushed into the Earth, and the simple argument is the Earth is molten in the center, 5,000 degrees centigrade, and all of that furnace has to be constantly fueled. You can't keep something at 5,000 degrees centigrade unless you keep throwing fuel in. It's like, you're on the Titanic and you have a whole bunch of people have to keep shoveling coal into the furnaces to keep the damn thing going. And the same is true for the Earth's heat. It has to be constantly fueled. And the fact is gravity is the fuel. Gravity is causing the effect because objects are, in fact, being pushed, crushed by the pressure in the external universe. The universe is full of cell phone calls, so to speak, lots of radiation. All of that radiation is constantly hitting matter, and it's constantly giving it momentum. And the fact is it's going to start moving towards each other, and clumping. So gravity clumps the universe. So it's completely opposite of entropy. It's clumping. Okay, so it's making it more organized and making it more pressurized. In simple truth, and the fact is that we're in that differential. The Earth. This exact moment, the force that would have stopped me from falling, see, can pretend I'm falling right now, but the force that would have stopped me from falling if I was above the surface of the Earth it didn't get to me, because it's got to go through the Earth and it's got to push a bunch of electrons, and so it's heating the Earth, and so it didn't get to me in time. It will, and a second later it'll show up, but it's always a second behind. So the force that's going to restore me to my position is always a second behind. So I'm always falling into that deficit. Pretty simple argument. Works. Then you have to explain drag and all that stuff. But yeah, that's also an argument where you could say, has anybody really analyzed how drag actually works, in the sense that can you actually change the fact that there's only so much energy on one side of you and only so much energy on the other side of you, and you can't really change those facts. It's like the electrons. They see each other based on a force between them. They can't change how much force is between them. They can just change how much compression there is. If I have a ping pong ball bouncing between two paddles and I move it closer together, the ball hits more often. Right? And if I have them further apart, it hits less often. So I can change how much pressure there is with the same number of components by just making the two surfaces closer to each other, further apart. Anyway, there's lots I could explain to you about gravity, but what it isn't is Einsteinian mush. So let's play the video and I'll just point out how this is just terrible, that they just turn a very simple subject into this complex, mushy bullshit about abstract perspectives, like somehow your perspective has something to do with the truth, when we all know our perspective is distorted by the fact it takes time for any for information to get to us. So we can't see the world as it is exactly now. Can't see the rest of the universe, right? All the stars are somewhere else. They're not where we're seeing them. Okay, none of them are actually where we're seeing them. So I mean, it's all, you got to know that's, okay, that's our bad. Okay, that's our brokenness. That's not the universe's brokenness. The stars aren't actually where we see them because we say so. That's where we see them. We know, because we're smart, they're someplace else, and we're being deceived. So there is no relativity horseshit. You can't force reality to fit your perspective. It is what it is. Things happen simultaneously because the universe, see, this is another thing, the time thing is so stupid. Every one of us is in the same time. If I take me and put me a billion light years away, there's the same number of photons, generally speaking, hitting me, right? The same amount of energy from the universe, the same background radiation, the same all this stuff. So I'm in the same clock. I can't be in a different clock. I'm always in the same clock. And if I move in this field of energy, the fact is, if I hit more stuff coming forward, well, I hit less stuff from behind. So the total amount of stuff hitting me, the total clock, is the same. The same number of photons are going through me at any one moment. No matter how fast I go, I can't change that. I can't change the density of the force. Because the fact is if I do go forward, I hit more this way, but I hit a lot less that way. So it always evens out. I can't change how much. The number of photons hitting me is the same thing as saying that's the clock. There is no other clock. Everybody's getting hit by photons, and we can't change how many are going to hit us, generally speaking. I mean, you go right next to the sun, and obviously you'll get burned to death. But I'm just saying, generally speaking, the average piece of space, you can't change the amount of stuff going through you. All right, anyway. Continuing.
When physicists talk about mass, they're normally referring to one of two things: gravitational mass, the one that causes weight, or inertial mass, the one that makes things hard to push.
All right, so this is the bullshit. There's no such thing. There's just mass, all right? And it just means bulk. It means the number of electrons and protons you have to push. So if you think of the force as being little hunks of Sisyphus, and you're just saying, well, I could, there's 10 atoms, there's 10 electrons. If I throw one Sisyphus at them, then he has to push all 10. So he's going to have a lot of mass to push. So he's not going to go very fast. But if I throw 10 Sisyphuses, well, then I'll go 10 times faster because, yeah, each Sisyphus can just push one boulder. So it's that simple, okay? There's no such thing as inertia. Nothing's saying I don't want to move. It's just saying you have to give me enough energy to move. If you give me, if you have 100 people and you give them one fish, they're not going to live very long, right? Okay, so you have to give them 100 fish if you want them to go, if you want them to all have a good day and have enough energy to move. But, that's all there is. You're just saying big things require more force to move because there's more atoms to move. Duh. There's no inertia.
In classical mechanics, it's not obvious that these two quantities always have to be the same, but in our experience, they are.
Yeah, and they are in any kind of rational perspective. There's just no way of arguing there's anything other in the universe than these atomic bits and your obligation to push them, and they push by exactly the same dynamic. So if you have 10 of them, you need 10 times the force. So when something falls the same speed in gravity, the feather and the hammer, well, the hammer has a ton more sail, so to speak, so it's going to collect a whole bunch more force, but it's also got 10 times the bulk. Okay, so it's going to go the same speed, but when it hits the ground, you'll see that it caught a lot more force, obviously, when it hits the ground. You'll see that it's a million times more atoms.
Another thing. If a thing has a half a kilogram of mass, that means that it has both a half a kilogram of gravitational mass and a half a kilogram of inertial mass.
So inertial mass measured based upon pushing something on a friction surface. So you should have explained that, like a pendulum. You should have just tied it like the other one you have tied. You could have just shown it on a pendulum and just say, yeah, okay, pushing it this way is going to take the same amount of work as pushing it up or down or sideways or any other direction. It's all the same thing once you understand, once you isolate out of the equation the obvious exaggeration of gravity that's caused by friction.
And from the first time that some early human ancestor picked up a rock and felt what it was like to wave something heavy around, until 1915.
Again, this is not even complicated in the sense that you can understand more bulk requires more fuel to move. You can't move heavier things with the same amount of force. You have to use more force to push more matter. I mean, it's just such a duh statement. To say Einstein fixed anything is just absolute bullshit, because he didn't fix anything. He didn't theorize any function here. There's no mechanism. It's some notion that there's some sort of bent nothing that creates frickin' momentum. And that's the key ingredient here, is that obviously gravity creates momentum. It creates energy. It gives things energy. And to say it gave it for free, that it didn't have to have energy to give the energy, well, I'm going to argue you've just broken physics. You have to have energy to give energy. You can't make something have momentum unless you already have it. So there has to be something that already has momentum, which is the fact that the frickin' universe is full of photonic energy, pushing everything all the time.
The reason that these two quantities were the same was a mystery.
So there's no mystery. Bullshit, bullshit, bullshit.
Today we're going to talk about inertia, and in a little while what general relativity has to say about the force of gravity. But I want to start this.
So he's really not going to get into any of that. And again, it's just this abstraction that you can pervert anything into a silly explanation. You can reverse the mechanism and say that some other thing is causing the effect. I don't know what an illustration of that is. You could just play anything like grass growing in reverse and pretend, but that's just pretending.
Video today with a puzzle about classical mechanics. Here I have two masses.
So even these words don't mean anything. This classical crap. When they use the word classical, they mean Leibnizian crap. Okay, it's not Galileo, Descartes, and Newton. No, it's Leibniz.
And a scale. And when I put one of these masses on the
so this is the part where it really irritates me, because here, okay, they're finally going to do the thing that I think is so revealing, and just figure out how much momentum the scale is reading. It's weighing. Weighing is momentum. You're saying how much momentum does this object have? That's what you're measuring, because you just turn the scale sideways and it'll measure exactly the same. And you'll find out that if you move something at 1 mile an hour into that scale sideways, that it will weigh its weight. Okay, that its momentum will equal its actual weight. So you know that what the scale is actually measuring is 1 mile an hour of velocity. Now, even though the object's not moving, that's what it's measuring. It's the same force. And it's because gravity is pushing that force in.
Scale, test mass A, we see that test mass A weighs 5 newtons. Classically, all massive objects feel the force of gravity. There is an
So let's say you don't feel gravity, right? Because it moves all your little bits, so they don't feel it. But the fact is that everything is moved by it, and it's actual movement. You're actually moving. You gain momentum. So if I drop something from a height and let it free fall, it's going to go faster and faster and faster and gain more and more gravitational force. So each second it gets 9.8 meters of velocity. So its velocity increases, and that means its impulse momentum increases, the force it will apply when it hits the ground. And this is all kind of obvious. The faster the meteor goes, the bigger mess it makes when it hits the Earth.
attractive force pulling test mass.
So there's no attraction forces, right? There's just pushes. You have a push from the open atmosphere above. Nothing's in the way for all the radiation from above you. Lots of stuff in the way for the radiation below you, okay? Really hard for the universe to get to you if it has to go all the way through the Earth and push a bunch of electrons. But it's really easy for the universe to get to you from above because there's just a little tiny bit of atmosphere above you. Duh.
Towards the core of Earth. And there's an attractive force
So it's really not going towards the core of Earth, it's going towards the other side of the Earth. And obviously all of the forces go through that middle, so the middle gets extremely hot because that's where all the forces are interacting and they're pushing against each other, you know. And so they're going left, right, left, right, left, right, left, right. And they're going to burn the tires. They're going to melt the tires on the car because they're turning left and right so quickly.
Earth towards test mass A.
Yeah, bullshit. Obviously these big giant things, okay, aren't going to be affected by minuscule things. So you could argue that it's doing that, but it really, you know, it's such a tiny effect that you'd say, you know, is it really even acknowledgeable?
And when we put a scale in between, those forces
So we know the force of the Earth being moved up by the tiny little block is so minuscule it isn't any part of this equation, and the only part of the equation is the differential being created by the Earth. The big giant thick Earth, the 4 or 5, 8,000 miles of electrons and protons that the force has to jiggle its way through, that's the differential that is doing all of that, that's creating all of the difference between the force coming down and the force coming up. So it has nothing to do with two things pushing from both sides. That's just bullshit, especially in this circumstance. One side's doing all the pushing.
Push the scale, and the force that scale exerts upwards on the object is the only thing that's preventing that object from accelerating down through the ground and falling towards the core of.
So there's just a point where you have an equal amount of tension, okay, and that's it. But the fact is when you put the object on the scale is a spring, it absorbed that energy. So that's in the scale still. It didn't get to the ground. So the ground never pushed back for the part that you've stored. Now the constant, every 1 second, it's still pushing. So you can't collect any more than just that one unit of weight in the spring. So the spring just has that 1 unit of weight. Can't collect any more over time. You can only collect that 1 unit because now all of the weight is going right into the table. And to say the table's pushing back is just as obvious as just saying you're increasing the pressure of the table. You're putting more pressure into the table, and the table's just pushing you back. The molecules on the surface of the table could be doing all the work. If I make the table out of rubber, you can understand that the elasticity of the rubber would do all the work, and maybe the floor would never even feel anything.
Earth. Now, if the scale were to exert more force than the object's weight, say 6 newtons, the object accelerates upwards. Shocking, I know. Now it's actually...
Yeah, right. So yeah, this is just completely uninteresting in the sense that, as you're moving against the gravity, that means you're going to absorb more of that differential because you're moving through it, against it.
fairly difficult to lift with exactly 1 extra newton of force. So here that is again in slow motion when I got a little bit closer to exactly 6 newtons. It's worth noting that while I'm pushing up with more...
So this is what they're using high-speed cameras to do. You know, instead of actually dropping the object onto the scale and seeing exactly how the scale reacts to the impact of the object, no, we're doing this instead.
Force than the object's weight. The object isn't just moving upwards, it's actually accelerating upwards. Its vertical velocity is increasing the whole time.
Okay, so its vertical velocity is increasing, but his hand wasn't moving any faster, so that's a little hard to imagine, but whatever. Yeah, so he's applying a constant 1. Okay, instead of 9.8, he's just applying a constant 1 meter per second of force to it, extra force. And so it takes a much longer time at that tiny amount. You know, you have to go 4 times the distance to get to 2 velocity, and then 4 times that distance to get to 3 velocity. So yes, the acceleration was it's so minor that you can't visually see it. You can only see it by recording.
Here is our second mystery object, test mass B, and I have it sitting on the scale, and the scale again reads 5 newtons. The only difference is that test mass B has this very suspicious string tied to it that goes up and out of frame. You don't know where that string goes, but you know that strings can't push. Strings can only pull. So right at this moment, you know that there is an additional upwards force on test mass B. But what's that additional?
So it really is pushing, but regardless, okay, I guess it can't push forward. I mean, you can't use it to, you can only use it one way. Yeah, I guess that would be the argument. You can only put tension in it in one direction. So that would probably be one way to say it. But regardless, all right. So obviously, yes, he's got a counterweight of some kind, and you know, this is actually weighs more than 5 newtons, but he's got something else absorbing some percentage of the weight. So not miraculous.
Force going to do? I'm about to lift up on this scale the same way that I did last time until the scale reads 6 newtons. Is the additional upwards force provided by this string going to make the mass accelerate upwards faster? Is the whole contraption somehow going to make the mass accelerate more slowly? Or does the extra force not matter?
Ew, I hate quizzes. Yeah, so I don't know what I would have guessed. I guess I would have said it's going to be the same, but who knows?
Does the force on the scale always cause the object to accelerate at the same rate? Anybody that wants bonus internet points, this is your opportunity to go commit to an answer in the comments.
Ah, fuck you.
Before I run the test. 3, 2, 1. So here we see.
I'm sure this guy hated quizzes in school, you know. Just wanted answers. Just give me the fucking answer. Don't quiz me on this shit.
5 newtons, and I lift with 6 newtons of force approximately. And
so we know that the speed you're going, you're still collecting gravity, right? It's still a time-dependent force. So how slowly you lift something is going to be. So he's doing a lot more work, right? The scale's reading the same number, but he's going to do more work.
There we go. It goes really, really slowly. Do you look at this and have some sort of intuitive reaction that something's wrong here? Because I sure do. What do you think this string is actually doing? We're going to zoom out very briefly and talk about 2 trips that I went on last summer that both involved very strange elevators. The first one felt significantly more rickety, but in reality was probably much more secure and was definitely much more awesome. This is Test Stand 4693 at Redstone Arsenal in Huntsville, Alabama. This absolute...
Who the hell would go here for what purpose? I don't know.
Massive structure is ridiculously strong, and it's used to squeeze sections of rockets until they blow up. The ring at the...
So that makes a lot of sense. Squeeze sections of rockets and then blow them. Why didn't you show us that? Because I don't really know why the fuck you do that.
Top has the most absurdly large welds I've ever seen. Everything about this place was justifiably, awesomely overbuilt. But maybe anticlimactically for this video, I am only going to be focusing on the two very sketchy elevators.
So I don't know. So there's two elevators in this thing, but you're only going to ride in one of them. So who cares if there's two of them? If only one of, if they're both the same.
It's refusing to focus.
Focus.
As long as you know there's one there. I mean, if you could do a pull-up and get yourself out of here, but yeah.
Ugh, that looks like a lot of fun.
Wait till we get to the bottom of it. Oh, God.
In case you can't tell from the clip, the noise that was coming out of this elevator was loud and not at all reassuring.
Wait, so where's the? Oh, there's the pinion.
That's why it's so horribly loud. This is a rack and pinion elevator. That means that there is no cable. There is no
It's gears.
winch at the top that's pulling the car up and letting it fall down. The car is climbing. The elevator has a motor on board and it spins a gear to lift itself, literally climbing up and down the tower by meshing its pinion with a very long rack.
So it has a whole bunch of gears, so it's spreading the load over a bunch of gears.
This means that at all moments in time, the entire weight of the elevator is supported on these gears. If the gears were to slip, the elevator would fall. If the gears were to back out of the rack and disengage, the elevator would fall.
Okay, and yeah, and there's little simple mechanisms you can create to prevent that from meaning anything, in the sense that there's little accelerating flippers you can have that will lock the elevator so it can't fall. So that's not a big deal. As soon as the elevator goes too fast, you can create a mechanism that just basically says stop. So that's not really an issue.
And there are, of course, forces resolved in this mechanical system trying to make both of those two things happen all the time. Honestly, a mechanism like this
I don't really think there are, frankly. I don't think there's all these about forces that are trying to shoot the elevator off of the gears. So there's just the forces down. There's not really a whole bunch of forces going sideways, but whatever.
makes sense to be used out here in the elements, where a regular cable may degrade when exposed to the weather.
So again, silly. Okay, obviously you could coat a cable. It's not that hard to put a coating on a cable, right? What's the catch there? A plastic coating on the cable? No, it's not really hard to do. Wax. You could just wax the cable. And the real truth is you could just have a second cable, right? So you have the main cable, then you have a second cable. So if the main cable breaks, the second cable grabs the load, so no problem. So what's the issue? Oh yeah, that's right, there isn't one.
Along with whatever cryogenics explode out of a rocket tank. But in general, this is an atypical design. When you want...
Yeah, and in general, it's kind of stupid because obviously, well, we don't even know though. Maybe there are counterweights that we can't see. So maybe he's wrong in the fact that maybe the elevator does have counterweights and it's just using the gears to, you know, make the slight difference in the motion, you know, to overcome the counterweight. So maybe it's a perfectly rational design. I don't know.
The elevator to go up, you not only have to apply a force to accelerate upwards, you also have to hold the entire weight of the elevator.
Right, that's the part where you're saying, yeah, so why not just use a counterweight and then you don't have to hold the weight of the elevator. The counterweight will do it for you.
In the intro demo, I was applying a 6 Newton force to the bottom of a mass to make it move up. But 5 of those 6 Newtons were just to hold it still. If I apply 5 Newtons, it just sits there. But if I apply 6 Newtons, it accelerates. And if I apply 7 Newtons, it accelerates twice as fast.
There you go. So there's no quadratic relationship there. So that's something to point out. I mean, I don't know how big a deal to make out of it, but right there he's pointing out that there's no quadratic relationship. I can get twice the velocity. I didn't do 4 times the force. I didn't do any of that crap. And I have twice the velocity. So, you know, maybe I can think of a way of taking this clip and capitalizing. Because, yes, no evidence of kinetic energy having a damn thing to do with it.
Because I've doubled the excess force. Now this elevator is
Right, double the force, double the motion. Not anything else, not 1/4 of the motion.
big chunk of steel. So the vast majority of the force exerted by these gears is just used to hold the thing in the air. And very little is useful work driving you upwards. Coincidentally, for this example, this is the same problem that rockets face, wasting energy prior to reaching orbit. But
Right, so he's saying this brilliantly engineered giant thing, they weren't smart enough to say we're wasting a whole bunch of electricity moving the elevators up and down, and we're putting a bunch of stress on the gears that we don't need to put on the gears, merely because we're not smart enough to create a counterweight. Oh, okay. Obviously, you can't do a counterweight for rockets, right? So, yeah, you're out of luck. No counterweights possible.
today we're just going to talk about elevators. This is the Como Brunate funicular in Italy. And the first thing that you'll notice about it is that the car leaves the station at a 45-degree angle, which is, needless to say, uncommon. If you stand here for like 10 minutes, you'll notice that the...
So this isn't much different than cable cars, except the cable's in the bottom instead of the top. So it's just like the ones in the air, you know, where you're going from one peak to another peak and you're on a cable. Same idea. I mean, I don't know if you call these elevators, but I guess obviously they change your elevation, so I guess they're elevators. But, you know, I mean, is one of those moving staircases an elevator technically because it elevates you? I don't think so.
car comes back a different color, which is even weirder. To answer the first question, it goes at a 45-degree angle because the elevator follows train tracks that are cut into the side of a mountain. And to answer the second question, the car...
So it could, you know, like I said, they're probably just using something because it's convenient, but I just mean, you know, you could just do the suspended kind of cars and do the same thing. So you could probably hold a lot more people per car without, you know, doing the suspended cable thing.
Changes color because there are actually two cars, and they pass each other in the middle with every trip. So why would they do this? Well, because they don't want the mechanism to have to hold up the entire mass of the car at all moments in time. The secret is that these cars very nearly counterbalance each other. There's a big pulley at the top of the hill and almost 1,100 meters of steel cable in a big loop. As one car goes down, expending gravitational potential energy, the other car goes up, gaining gravitational potential energy.
You know, this whole gaining and, you know, obviously you can't gain energy. It's like saying a boat on the side of the river has energy, and it really doesn't. It only gets energy when it goes into the stream. So it's just saying you're going to put something and allow it to fall in gravity, and then you're going to put something that doesn't fall in gravity. I mean, you can't, there's no potential bullshit.
If you stand near the drive pulley at the top, you can see this really clearly. This car just started going down. It's attached to this cable. And the other end of the cable, with another car tied to it a kilometer down the hill, is just beginning its journey towards the top. If both cars weighed almost exactly the same, you could drop a kitchen scale underneath the car at the bottom, and it would read a lot less than the mass of the car. But if you pushed on that scale and applied only 1 additional newton of force, you'd be waiting a long time for that car to accelerate. Because despite having an apparently low weight, it's still really massive.
So again, it doesn't have a real low weight, okay? Because obviously the weight is being controlled by some other mechanism, and so you're not seeing that weight, but you're going to see it as soon as you try to change its weight. As soon as you try to change its motion, you're stuck with moving all of the atoms.
Still has a lot of inertia.
So it's not a lot of inertia. It has a lot of mass. It has a lot of bits that have to be moved, a lot of weight that has to be moved, a lot of stuff it has to move. So if you apply a small force and it's spread over all that stuff, it's going to be a tiny, tiny influence, obviously.
Huge nerd, but the whole time I was watching this, I was flabbergasted by how brilliant of an idea it was. And then I thought about it more, and I realized that all modern elevators have counterweights. You just don't normally get to ride in the counterweight, which is unfortunate because this setup makes for such an awesome visual demo of what's happening.
Would it really make a difference if you could say, I'm in the counterweight? I mean, how would it make any difference? I mean, if you really could see the other elevator on the other side moving opposite you, would it mean anything? No, I don't think so.
If the script worked out the way I wanted it to, the intro from...
Funny they didn't ride and actually videotape the part where the two pass each other, because that would be interesting, right? That's the only moment where you get this idea that, hey, look, they're going down and we're going up and we're opposite each other and we're countering each other.
Example now looks pretty trivial in the face of these two elevators. The second mass
So all of this seems pretty trivial so far. That's right. It's just grammar school kind of crap, and you know.
is more difficult to accelerate because it has more mass. It is heavier, but its mass was offset by a counterweight. This setup where you've got two masses both experiencing Earth gravity.
I don't know why the counterweight is that preposterously large. I mean, why wouldn't the counterweight be something similar to the same weight? I mean, your pulleys can't be that bad.
Connected by a pulley on the ceiling is known to physics students as an Atwood machine. Although ideally it's a frictionless pulley, and here I can do things like that, which is not great. When you just zoom in and you look at one end of the machine, it appears to cheat gravity because this object actually weighs a lot, but it doesn't require...
Why don't you give us some real weights? He says it weighs a lot. I mean, why don't you tell us how much weight is in the bucket and how much weight is this object? Because technically they probably should be the same weight to have a real Atwood machine.
That much force to support the object at this end because a lot of the weight is taken up by the counterweight over there. That bucket is countering some of the weight. Yeah, maybe that was obvious. So
yeah, it's countering all of it apparently because yes, this doesn't move. Yeah, so I guess it's countering all of it. Duh. Oh shit. My mistake. Zoom, 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 zoom. Nope. Zoom, zoom. Nope. Somewhere around here, somewhere. Okay.
Although ideally it's a frictionless pulley, and here I can do things like that, which is not great. When you just zoom in and you look...
So he says it's frictionless, and then he says, okay, so ideally, but the only reason why it would move is if the bucket has more weight in it. So again, he didn't explain. It shouldn't move if they're just the same weight.
At one end of the machine, it appears to cheat gravity because this object actually weighs a lot, but it doesn't require that much force to support the object at this end because a lot of the weight is taken up by the counterweight over there.
There's an equal tension already applied, right? So you can apply a force without having a counter force, without having to overcome the gravitational force that already has been countered by the counterweight.
That bucket is countering some of the weight. Yeah, maybe that was obvious. So counterweights can sort of let you cheat at gravity, but they don't let you cheat at inertia. And if anyone in the comments knows how to cheat at inertia, please let me know.
So the inertia is that you're still fighting gravity. So it isn't about inertia. It's about the fact that you're going to force the object to now gain momentum. And to have momentum, you have to give it a force. It's not for free. You can't get free momentum. And you're going to get that momentum by opposing the gravitational force. So obviously you're going to have to do some work.
Because I would love to go visit Jupiter someday, and being able to cheat at inertia would shave a lot off the travel time.
Rocks.
I don't think it would shave off anything off the travel time, because the travel time is dictated by what you can tolerate as acceleration, right? And then the fuel is the only problem, right? The travel time isn't the problem. The travel fuel is the problem. But let's just say you have your nuclear fuel or something like that. The point is you can't go infinite speed. You can't go ludicrous speed. Because you can't take it, the G-forces. So how fast you go doesn't have anything to do with it, frankly. So he got that part wrong, too. All right, we don't need these commercial shit.
Paper on them. This is a lasting sign between me and break.
Inertia is like a resistance to acceleration, but you need to...
So again, there's no resistance. You have to give something energy for it to have the energy. If you don't give it anything, and no sisyphuses are allowed through the doors, and then yes, nothing moves. Allow the force to go get the boulders and push them, then things move. And you need enough sisyphuses to move all the boulders you have. I mean, it's just not that complicated. It's like fertilizing plants or something. If you don't have enough fertilizer, then yeah, the plants don't grow as much.
Be careful with how you apply it. Here we have two people separated by a distance of 1 meter, and then, for some reason, the distance between them increases to 1.5 meters. Clearly one of them accelerated, but who? Okay, that's kind of obvious. It's the one on the left. But what if I take away the background cues? Okay, maybe it's still obviously the one on the left. But now, what if I also accelerate the camera? Is it less obvious? The one on the right experiences a coordinate or spatial acceleration.
So all of this bullshit to try to imply that something other than what we know to be the truth is the truth. I mean, we know what happened. We saw it, and we also have that visual clue. So why are we pretending, well, we can distort it enough until you can't tell? Well, so what? Does that mean you changed anything? No. Does that mean that guy didn't do the moving? Well, no, it doesn't mean that. Oh, it's just so ridiculous.
Visibly moving within our reference frame. But we can see from the pendulum that the one on the left, despite apparently standing still, is experiencing an acceleration. And we call this a proper acceleration. In the absence of any context, physics relies on the local experience of an observer to answer the question.
So this is the silly part. Well, why is it relying on observations that you already know are corrupt? Is there any point in me looking at a star and saying that's where the star is right now? No, we already know it's not there. So why are we pretending we don't know that?
Who's accelerating? And if the coordinate acceleration, the visible motion of stuff, lines up with the proper acceleration, the forces and acceleration experienced by those objects, then we say that we're in an inertial reference.
No, just babble. I mean, there's no frames that you can be in that mean anything. There's just optical illusions, and that's all there are.
Frame.
You're just being fooled by some optical event where something happens and you can't tell that's what it did because of the angle you're looking at it.
Because inertia works properly in this reference frame. The trick is figuring out where you need to put your camera so that you know that you're seeing an inertial reference frame.
Right, and you're claiming that the inertial reference frame has to do with what you claim you should be seeing, when obviously I would argue that the only frame that matters is the frame that gets the right answer. But whatever.
And not one of the weird accelerating reference frames. So what happened in 1915 that miraculously makes sense of this mess?
Bullshit. So it didn't make sense of anything. Bent nothing is not making sense of anything. That's not an answer. That's voodoo. That's spooky action.
Einstein happened with his general theory of relativity. I'm sure many of you in the audience are aware of fictitious forces and how sometimes they can be counterintuitive, but I would argue how they can be extremely useful. So bear with me.
So this is the big bullshit. Okay, so it's an advantage to pretend it's a real thing for doing some mathematical shortcut, but does that have anything to do with the truth? Oh, no, it doesn't. Okay. I mean, so, these pleasant delusions might have some advantage, but is that what science is supposed to be about, is useful delusions? No. It's supposed to be about accurate statements.
Through this first example. Here I have a camera pointed at a marble in a box. At a certain moment, I'm going to turn on a fictitious force and pull the ball to one side. Olimar clearly knows what's about to happen. And there, the ball suddenly accelerates to one side of the box and bounces lethargically against the wall. Isn't that incredible? The ball moved sideways.
Yeah, and that image isn't the same as the image he's going to show in a minute, because it didn't bounce more than once in the other image he's going to show, but whatever.
Okay, now before we designate this the most boring physics demo of all time, let's look at that again from a different perspective. From above, this is what actually happened. The box was just traveling in a straight line and then suddenly started accelerating into a circular path. The ball in the box basically just kept going in a straight line, but from an observer inside the box, it looked like it was pulled by an unseen and inexplicable
we can't see.
force.
Okay, yeah, he's not going to
look at the motion of the ball carefully.
All right, so we didn't get to see it continue.
willfully. And the only real force that ever acts on the ball was the force applied to the ball by the wall of the box after the ball bounced. And that force actually points towards me in this demo, the center of rotation. There is no force that makes the ball move towards the wall of the box. It just has inertia, and it's moving in a straight line because that's how inertia works. An object in motion will remain in motion unless acted upon by an external force.
So the part that's a little bit dicey is how did he accelerate the ball? That is, give it the same velocity without it moving backward when he pushed the box. So I guess that's what the tape has something to do with. I don't know, there had to be something. He had to be so carefully to gain velocity. So he gained velocity very slowly, so the static friction kept the ball on that blue carpet. So he had to gain the velocity very slowly so he didn't break the static friction. Because the static friction, because then the ball would have just gone backwards because he's moving the floor underneath the ball. So he's not really explaining all that he did here. I mean, to create this illusion. So the illusion starts with moving the box very slowly and then get the ball up to this speed and then turn the angle at which you're going to accelerate. And so the ball has its old acceleration that you gave it carefully, slowly, and now you're going to jerk it with a hard acceleration to the right. So that's the difference.
Of course, in this real-world example, there's actually a small deviation because of friction with the floor of the box causes the ball to divert upwards slightly, and it loses some translational kinetic energy into rotation.
So there's no translational kinetic energy. So there's no kinetic energy anywhere. Just momentum. Yes, obviously it lost some momentum, and yes, like he's saying, there's a little bit of distortion because there's some friction with the floor. Duh.
Kinetic energy, but it's extremely close. From inside the box, it only looks like the ball is experiencing a sideways force because the whole reference frame is accelerating. There are multiple so-called fictitious forces that one needs to keep track of in classical mechanics in order to make sure that if the reference frame is accelerating, they're still doing math that makes sense.
Whatever. There's a ton of variables in every experiment. You got to figure out all these fucking variables. You got to figure out like even a spring, the simple argument that springs collect energy really well, but they don't give it back so good. So if you're going to use a spring to launch something, you're going to have to recognize that some percentage of your energy is going to be trapped in the spring and you can't get it out. The spring is going to keep moving after the thing you shot left. And so obviously the spring is going to wobble and oscillate, which is going to be an indication it didn't give away all of its energy. These are little facts, okay, that make all of this analysis something you got to do very carefully.
But the centrifugal force, the one that I've just demonstrated, is far and away the most popular to discuss because at some point everyone has been spun in a circle and felt like they're being thrown out away from the center of rotation. Oh, God. Okay.
Well, they are, in fact, being thrown out. That's where your momentum wants you to go. That's the straight line, and the other force has got to counter it. So, obviously, it is technically real in the sense that that's where the mass wants to go, in the sense that it wants to stay going in a straight line, and you're going to force it to bend.
Now I'm nauseous.
And you're not going to force it to bend by an external force. In this kind of case, you're going to force it to bend based on the tension inside your body. Your muscles are going to hold yourself together. You're going to apply the counter force that's going to allow your straight motion to be a curved motion.
That was really stupid. The centrifugal force is also extremely popular amongst internet commenters who say that actually fictitious forces aren't real and shouldn't be a thing, but I disagree.
So I disagree that anytime you're using the word fictitious or fake or deceptive or illusionary or some other kind of term, well, fuck that. Let's try to get to the truth.
Know how to use them. If you have a convenient reference frame and you construct the correct fictitious forces, you can get the correct answer.
So that's a real question. Do we get any correct answers? Especially with the kinetic energy formula. Is it really correct that they're measuring real things? So, you could go through the rocket equation or all kinds of things where all I do is I change the mass of the rocket and all of a sudden the the fuel in the rocket has a different octane, has a different ability to produce energy. It doesn't make any sense. How can I make the fuel have more energy by pushing a lighter rocket? That's idiotic. Everybody should admit that's idiotic.
While doing a lot less math. A good physicist is lazy, and knowing when to make approximations and when to make...
Yeah, approximations are fine. You're just talking about pretending, creating a fake model that isn't accurate because it's convenient and shortcutty. But you're conceding it could be very sloppy. I suppose that's where you get into all these infinities, right? They have a bunch of mathematical formulas that don't work very well at the extremes. Very light things or very heavy things, everything falls apart. Well, yeah, recognizing that you can't use it in those circumstances. So you could say MGH is a real thing. And I could argue, well, no, how you know it's not a real thing is the fact that it doesn't work in all these other circumstances. So as soon as I give something a velocity as it goes into a gravitational field, MGH won't give me the right answer about how much energy I'm going to get from gravity. He'll give me the wrong answer.
Coordinate transforms that aren't even approximations, or just different ways of thinking of the problem, is really important. But what does this have to do?
Yes, exactly. What does it have to do with gravity?
With gravity? Well, we're in the box. This marble is not accelerating towards the ground.
So we know it is, okay, and we know the ground is stable because we know the atoms of the ground are all connected to each other. So the table is connected to the floor is connected to the ground goes down deep, 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 and all of that stuff isn't getting bigger. It isn't expanding. Okay, so nothing's accelerating that way. Okay, exactly the opposite's happening. It's being compressed constantly.
Everything else, me, the ground, the table, the camera, is accelerating upwards right now at about 10 meters per second per second.
Yeah, just bullshit. So why they do this? I mean, why they do something that is that easily proven to be nonsense? We know that that anvil right there, there's the atoms aren't spreading. There's no place for this acceleration to happen. The center of the Earth isn't expanding out like there's a vacuum inside there and the ball's getting bigger and bigger. There's no place to make your expansion. So to say you're creating more distance, you can't create the more distance because all the atoms have to be connected to each other and you can't stretch them. And there's no reason they would stretch. So it's a silly theory, easily debunked.
Bear with me. Gravity, the nice, friendly, Newtonian, classical gravity that we all know and love, is a fictitious force.
No, it's just so silly. You know, it's this powerful force that's creating all of this motion in the universe and consolidating objects. So again, they have this silly theory that the universe is running out of. It's turning into little bits flying out, and we're going to all die of a heat death, right? The universe is going to run out of energy. When at this very moment, the universe is constantly compressing objects and making them smaller and more compact and more dense. It's constantly doing it. I mean, it's just amazing that they can make this argument. It's constantly creating the fuel of expansion. It's giving you the fuel to have an expansion.
This is what gravity looks like in the reference frame of Earth's surface. Stuff falls. This is what we're used to.
So the word fall doesn't mean much. Stuff gains momentum. So it's given momentum. It gains actual momentum. All right? It's a real force. It has real moving. It's moving, okay, with a force. Newton would say twice the force, twice the motion. 3 times the force, 3 times the motion. It's a real thing that's happened to it. It's gained real force. It's carrying it. It's a force carrier now. And when it impacts something, when something has a trajectory that is in conflict with it, you will see the force it has collected in terms of you'll see an event that may be explosive.
Now let's zoom out to a true inertial reference frame, and this is what gravity looks like. The beanbag is just either not moving or moving at a constant rate, and suddenly the ground comes up and slams into it. How rude. I also need to point out that intentionally putting the most expensive objects that I own into freefall repeatedly was terrifying.
Don't like this at all.
Yeah, whatever. You're making enough money. Yeah, so sure, what a pile of shit. Oh, yes, I'm worried about it. Yeah, right. Disgusting. Anyway, continue.
When you are free falling in a gravity field, that is actually an inertial reference frame, like a skydiver.
So all he did was put a strap around the camera so he could just move his hand faster, okay, then the camera could fall, so it would free fall, and then the strap collects it. So what's the big deal? Not a terrible threat.
A vacuum, or someone in orbit around Earth that's continuously falling. Those are actual true inertial reference frames. And any acceleration within this frame must be felt as a force. It's pretty hard to see in this.
So again, felt as a force. We know we can't feel. You can't feel a force that moves all of your bits exactly the same. So a force that moves this the same speed as it moves this, as it moves this, as it moves this, I can't feel that. But a force that moves my feet first, okay, and my head much later, that I'm going to feel. So I have to create some sort of tension inside the object. Gravity doesn't create any tension because it moves every electron the same as every other electron. They all move the same speed.
Because your brain takes cues from the background and you know the camera is falling. So here, if I remove the background, you can see that after the beanbag is released, my hand accelerates upwards, propelled from the force on my feet and transmitted through my body. Then we're just looking at a beanbag at rest in an inertial frame. Nothing weird about that. And then the table comes along to accelerate the beanbag within the inertial reference frame. It's kind of a bizarre way to think about it.
It's a silly way to think about it because we actually know better. So that's all I would say. It's obviously not correct. So you want to pervert it and pretend you could do that. But that's just pretending.
If you want an example to compare to, think about this sideways, so we don't have to care about gravity. The object is at rest, and then a force.
You're just saying you have a force differential. One object there is going to have a difference than the other object, and so the force differentials are always the same. But the argument would be is if you actually calculate the momentum in an object, right? So if I have a P moving with, a tiny bit of force versus a big object that has a lot of force to move the same speed. So I'm going to have an incident, an event where they're both going to collide with each other. It's really going to matter whether one of them, the heavy thing's moving, the outcome of the experiment will be different than if the light thing's moving. So they keep doing this with masses that are too equal. So if they did it with masses that are broadly different, the two experiments will be different. You'll see the difference between the tiny amount of energy that a small object moving 10 miles an hour, right? We're saying the collision is going to happen at 10 miles an hour. That's a given, regardless of what object we think is moving. If this one's moving, it's 10 miles an hour. If this one's moving, it's 10 miles an hour. They're going to meet at 10 miles an hour. And so the question is if it's a tiny object, it's going to be a tiny amount of energy. If it's a big object, it's going to be a gigantic amount of energy. So they won't react the same way. One of them will cause a reflection. The other one will cause the motion will just keep going in the one direction.
Force is applied that causes it to accelerate. In this particular case, it's the
There is no equivalence. If they really picked at this, you could find that there isn't real equivalence.
normal force that the ground exerts on the object that's doing the true acceleration, accelerating the beanbag upwards. Oh.
So we're just saying the collision happens, right? So the beanbag is collecting the energy all evenly across its entire shape, so we don't see any evidence that it's going fast. But it doesn't really matter. But again, that's because they're using two things that have similar masses.
Away from Earth's surface. Comparing to the centrifuge example, the only real force applied to the object, the only force that results in a proper acceleration, is when the object hits a surface. In both the centrifuge case and the gravity case.
Yes, you can only test how much energy something has by having it hit something. Yes, that's right. Photons have to hit something for you to measure their existence. You can't measure something's existence or what it is until it hits something. Yes, that's the only way you can measure things. Yes.
When the object starts moving in the local reference frame, it's because of a fictitious force. And therefore, when that object eventually hits something, and that something else applies the force that keeps the object in the accelerating frame, it's actually in the opposite direction. This bounce, or the force of the floor or the wall here, is what actually keeps the object in the accelerating reference frame. So kind of
Whatever that could possibly mean. I mean, obviously the bounce is a byproduct of the fact that the object is elastic and it stored a bunch of energy and then it released the energy. Okay, once it was equalized, the pressure.
by definition, it has to be opposite the fictitious force that's trying to get the object to leave the reference frame. I think this is a...
The only force opposing its motion is gravity. Okay, and so it gained a whole bunch of gravity going down, and it's only the opposing force is only 1 unit of gravity. So it has to keep hitting another unit, so it can't stop until it's gone through as many units, that is seconds of gravity, that it took to fall. So until it's been in the same number of gravitational units, that's when it'll stop moving, but it can't stop moving until then.
really difficult thing to grasp, because our human brains are hard.
If it falls 5 seconds and it's got 5 seconds worth of gravity, it's going to take it 5 seconds in gravity to lose that momentum. Now, if I make it a hard object, not an elastic object, then it'll just hit the ground. It can lose all the energy at once. So it'll do 5 times the work in 1 unit of time.
Wired to exist at 1g. We always feel like we are being accelerated, pushed through.
So I don't know why he says that's what he feels. I don't feel any of that. I don't feel like I'm being accelerated up. I feel, okay, the fact that I'm being pushed into a surface, squished into it. That's how I feel it.
Our feet upwards at 10 meters per second. And that's not weird, because it's what we're used to. So here's a way that you might be able to train yourself to feel this acceleration. When you stand just on the ground, there is a force on the bottom of your feet.
It's a lot easier to feel it on the bottom of your ass when you're sitting in a chair, especially a hard chair. No problem.
You don't notice it, but you can feel there is physically a force on the bottom of your feet. If you sit down, your feet no longer feel that force. In fact, if you've been standing for a while and you sit down, you might even feel your foot like swell out. Your feet are getting less compressed, just like that spring scale. Now, if you lay sideways, you can experience the same.
Yeah, we're really unelastic, okay? I mean, we're elastic, but the elasticity is very slow. So our whole spinal cord is being compressed, and you could go to sleep and it will re-expand again. So you get taller, and you're taller in the morning than you are at night. So what? But I'm just saying that's a real thing. It's real compression. You've stored some energy, but it's a tiny amount.
Force on your feet, say, if someone pushed you, accelerating you sideways through our customary reference frame here on Earth's surface. That force on your feet causes you to accelerate, always. The real kicker here.
So no bullshit. So obviously these are very different forces. I'm just saying, obviously, matter that has collected momentum pushing on you is different than a force pushing on you directly. Gravity is a direct force, okay? A rock being thrown and hitting you is an indirect collection of force. It's still force, but obviously it's going to interact with you in a completely different manner. It's not going to move all of your matter the same speed, where gravity will.
Is that when you're standing up and you feel that force on your feet, it's also causing you to accelerate in an inertial reference frame. This is why inertial...
This is silly. You're not accelerating up. Oof.
Mass and gravitational mass are the same thing. If I wanted to...
I mean, look, you could argue simply that you don't feel gravity, so you don't feel gaining motion downward. So you're downward, you're pushed into the earth, you don't feel, and you just feel the earth rebalancing the pressure. So technically, it's a little tiny acceleration, and then you're re-accelerated down again. The only one you're feeling is the one going back up. So I suppose you could argue that, but I don't feel it, frankly. It's not what I sense. You could argue that's what's actually happening. Where the fuck is my voice gone? Well, anyway, I'll take a break, see if I can find it. Yeah, it should be back. Continuing.
Are the same thing. If I wanted to accelerate an object sideways, I would need to apply a force. And the more massive that object, the larger the force I would need to apply to accelerate it at the same rate. That's inertia.
Right, so why doesn't he do that experiment, right? Just turn the scale sideways and see how much motion, how much momentum it takes to make something read its weight, and see if for every single object is it exactly the same speed. And yes, that's what will be found. It'll always be the same speed.
In our falling reference frame, the weight of an object is the force necessary to keep that object pinned.
So yeah, you can almost see the scale there, but yeah, probably not enough to see. But the fact is if you do this frame by frame, the crushing of that stuff he put on there to protect the scale does change it, so it doesn't quite read. So it's only reading 1 Newton now, a little bit less. So it's already started to hit stuff, but it isn't measuring anything because the stuff it's hitting is collecting the force. And it's not until that stuff stops collecting the force that the scale starts to read the actual weight. There it goes. So yes, it will do exactly as I pointed out. It'll go all the way to 9, almost 9. So it's collecting the object's weight. It's going to collect an impulse weight that's going to be proportional to the distance, okay, that it dropped, but the distance it dropped is really time. So the free fall time and how much gravity it collected in that 1 meter drop is enough to have it weighing 8 times its normal weight. 8.5, 9, something like that.
In this reference frame, the object must be continually accelerated, and more massive objects require more force to accelerate them at the rate of gravity.
So we know that the gravity is it's collecting more because it's the same wind blowing on sails that are different sizes. So if you're a heavy object, you have a lot of sail. You're a light object, you have a little tiny sail, but it's always proportional. So it's always going to make you go the same speed. The light thing goes the same speed as the heavy thing because the heavy thing is just made of a bunch of little sails that are the same size as the light thing's sail.
In the lab frame, that means that they look heavier. We see there's an initial large force at impact, but once that settles...
So he said a large force at impact. I mean, this is real physics. This should be actually calculated by somebody and measured by somebody. Exactly what is the force? 1 centimeter, twice your weight. 4 centimeters, 3 times your weight. Twice your weight. Twice the single weight. So it's actually twice plus your weight. Okay, I have to keep saying plus 1 unit of weight. And then, 9 times the distance is 3 times your weight plus the 1 weight, your actual weight.
It's measuring the weight of the object. This is the force necessary to continuously accelerate an object within an inertial reference frame at about 10 meters per second, or...
Right, and then so you could just measure how much you actually gain, where you actually weigh your weight with a force going horizontally, and that's the 1 mile an hour thing. So 0.44 meters per second, a lot less than 9.8 meters per second.
1G.
Hey, we got this old mattress.
Waterbed.
And the receipt.
How about you beat it with a better deal on one of these fresh setups?
I don't understand this.
If this sounds really weird, you may accurately say, but I'm not flying off into space at 10 meters per second right now. What's the big deal? I'm telling you that you actually are accelerating away from Earth right now. It's just that space itself is actually falling towards Earth at the same rate, so you don't go anywhere.
So how is that possible, though? I mean, just saying, how can those two things compensate for each other in any rational way? So you're actually saying that the compression of space is somehow compressing atoms or something from long distances or whatever? I mean, this is where they make up this idea that space is expanding so it can be compressing into material objects. So there's space being made out in empty space, and space is being consumed inside of material objects. I mean, the whole thing is ridiculous. When it's so much easier to just say the complete system is that there's pressure, little bits of ball bearings flying through space at the speed of light. They're constantly hitting everything, okay? And the fact is as they hit, they're shadowing each other from each other's impacts, and so they end up just being pushed right into each other. And that simple explanation solves the problem, frankly.
General relativity states that massive objects actually warp four-dimensional space.
Okay, so there's no four-dimensional, and they're just going to cheat and take away one of the forward dimensions and call it time, and it's just cheating because it's time isn't a 90-degree angle to the other two dimensions. That's not what time is. So the whole thing is just bullshit, useless bullshit, frankly.
That would be X, Y, Z, and time. And that's impossible to...
Yes, exactly. It's impossible because it's stupid and it's outside the definition of what a dimension is supposed to be, which is 90-degree angles to the other three dimensions. So if you can't have 90-degree angle to the other three dimensions, then you really can't exist as a thing.
Draw, which leads to many different depictions and interpretations that each...
Yeah, none of which have anything to do with the truth. So you'd end up bending a fabric and pretending using gravity to illustrate gravity, and then you do these silly drawings of dent things, and it's not three-dimensional, and the whole thing is just crap. Because what you're claiming is that matter is a vacuum cleaner, and it constantly pulls in, and somehow it ejects out over there. So somehow it throws everything way on the other side of the universe so it can suck it back up again somehow. Somehow you're pushing pressure out there, when the simple cycle to understand is the fact that, the fact is that gravity creates heat inside the Earth. The Earth radiates that heat eventually back into space, and that compresses everything again. So it's just a complete cycle of heat. It's just thermodynamics. It's just you're pressurizing matter in one place, and in some other location in space, you're expanding it again. And that's all you're doing. And that makes perfectly good sense. You compress, and then you expand, and you compress and expand and press, and that's the cycle.
Normally capture part of the intuition that you need to really work with this stuff. Let's just look at a 2D slice of space, and we'll add a third dimension of time. So we've removed it.
So yes, you removed the actual dimension of forward and back. Okay, so you still have up, down, and left, right, but you got rid of forward and back and called it time instead. So it's just bullshit.
We can draw it now. If we add a really heavy thing below us, space-time is literally curved down towards the Earth in such a way that a single reference frame appears to fall. Like, it's curving,
says you,
in time, but if you freeze one location in space and you look at the same frame after multiple time steps, it kind of looks like it's falling. It may not be exact, but my favorite way to think about this is literally to imagine falling reference frames anywhere.
Oh, whatever. Yeah. No, not for me, thank you. I like different kind of porn. Not that one.
Because the physics are the same for a reference frame moving at a constant velocity, you can just pop a reference frame into existence.
See, it's so easy not to do it that way. Alright, so let's get this done with. So the rest of this video isn't going to be worth watching, but we'll just speed through it as we can. Because, yes, it's all this abstract nonsense that somehow we have to believe that the universe is expanding or something. It's just the Earth is somehow getting bigger and accelerating us. I mean, if the two things are compensating for us, then there wouldn't be any gravity. So, of course, there is gravity, so two forces can't be compensating.
At zero velocity and watch it fall. And that's like a totally valid frame. If that helps you solve a problem, great. Remember that these falling frames are true inertial reference frames. An object in free fall, feeling no forces, will move at a constant velocity through one of these frames. And when it hits the ground, it has to accelerate. In order to exist on Earth...
So some of this you could prove, right? If we could make some big object in space and we could have it shaped where it's longer than it is thick, we could figure out that the gravity on the thin part is less than the gravity at the length part. And so, recognizing that this is a real force that you can moderate by changing the arrangement of the matter. And the Earth already proves it, right? I mean, the gravity is a little bit different at the poles versus at the equator. So it's already proving the point that this gravity phenomenon is really affected by how much mass there is between you and the other side of the Earth.
Surface, any object must be continually accelerating up through one of these inertial frames with a force proportional to its mass, also known as weight. Granted, saying that space is falling is a little bit of a stretch because it actually is this curvature of the time axis. And in order to make this...
Yeah, baby talk. Just mush. Silly crap. The curvature of the time axis. There's no axis. There's no time axis. There's no such thing.
That space is falling, I'm sort of ripping the time axis off of 4D space-time, which is not how it works.
Yeah, it's not, and you didn't even do 3D, right? You changed 3D into 2D and put time in as the third dimension, which it isn't. So yes, you're cheating all over the damn place.
In Newtonian physics, we like to show what forces act on what objects and use that to predict how they accelerate and move.
Yes, and it's per second. It's a time-dependent force. You get it in units of seconds.
In the falling reference frame formulation, we're still really doing Newtonian mechanics. We're just adding this accelerating reference frame because it forces inertial mass and gravitational mass to be the same thing. And while this is accurate, it is an approximation that only holds in friendly, even gravity fields like here on Earth's surface. Taking this formulation too literally implies that you're like gradually accumulating some physical material called space-time near massive objects. It also doesn't stop you from doing obviously illegal things, like accelerating an object within one of these falling frames past the speed of light. Say you were dropping it from really far away towards something that was really dense. So the visualization, however helpful I find it, is still incomplete. To solve real problems in general relativity, physicists forgo Newtonian mechanics altogether in favor of calculating something called a geodesic. A time-like geodesic is the path an object will follow through space, subject to the curvature of space-time. And while calculating one of these is very complicated, it doesn't require you using any forces, real or fictitious, and it doesn't require any accelerating local reference frames. The first experimental evidence for general relativity was actually gravitational lensing.
So yeah, the big fake image of the lensing. So here we are, just more bullshit. So they can't be anywhere near the truth, right? So it never was anything you're seeing it get lensed from some invisible point behind the sun. That has nothing to do with the experiment. So again, just complete shit. Oh, I didn't know he's going to throw in this silly image of lensing. We're talking about a tiny, tiny deflection, and the fact is they've never done the experiment from space. 400 times better viewing from space, and they've never repeated the fucking experiment. It takes 5 minutes and you don't need an eclipse, and they haven't even attempted it. And he's going to keep telling me I have to believe that shit. That absolute crap. The guy in his own journal writes, I wouldn't stake my life on these results. And why does he write that? Because he got 10% of the data quality. Looking for 10,000 stars on his photograph, he got 1,000. 1/10 of the quality. And that experiment is supposed to be pristine, and we're all supposed to believe this bullshit happens.
Gravity alters the path of light. Notice the path that light takes here. Within the falling reference frame, the light continues in a straight line, but from our outside view, it looks like it curves around the sun.
What a pile of shit. It has to curve around the sun, so I don't know what this look like shit is. It either is or isn't bent. And the simple argument obviously is it's not.
Although I'm showing it with light, this is how it works for any object. Planets, satellites, a random asteroid swinging by the sun in a hyperbolic orbit, all of these objects get caught up in the reference frames falling towards the sun when...
So there's a real force, yes, so you don't need to make this fake thing up. You can just say there's a real differential between the energy coming out and the energy going in, and that'll create exactly the same math. It'll be exactly the same. You can't change it, okay? It's the same mechanism. It's saying you have the same amount. It's an inverse square law. It's mathematically rigid. So playing a game and pretending it's some other magical thing that's causing the flow is bullshit. So when Leonard Susskind teaches this stupid subject of relativity, he uses fluid as an example. He says there's water. There's a waterfall way out here. It's producing water pressure. The water pressure is going to be going into a drain in the center of the earth. That's how he's describing gravity, for fuck's sake. He's using mock gravity as an explanation. And mock gravity is what I'm arguing, is real gravity.
Get close. And that causes their path through the space that we observe to bend. If you calculate just the acceleration due to Newtonian gravity by canceling out the masses, and then applying that acceleration to light, you can get to what is mathematically identical to the falling reference frames approximation that we've made here today. That as light is traveling past a massive object, it passes through a falling reference frame, and the light is deflected. But if you only calculate the motion of the reference frame using Newtonian equations, you get the wrong answer.
No, so there's no fact that you get any wrong answer. So again, it's an inverse square law. There's no way you can get a wrong fucking answer. So that's just bullshit. I mean, that's bullshit. There will be no example showing us how you get a wrong answer if you recognize that Newton said inverse square law. Because that's all there is here. There's nothing else to it.
Famous Eddington experiment during the 1919 total solar eclipse, the question the scientists were asking wasn't, does gravity bend light? They were asking, how much does gravity bend light? And by looking at the light from stars that was deflected by passing close to the sun, they were able to conclusively show...
They conclusively show, right, in an experiment where he claims, I only got 10% of my data quality and I wouldn't stake my life on these results. And that was conclusively proven. Yeah, fuck you. I mean, to recite this lie that this experiment is the greatest achievement of mankind and it's been done so well, and then to say in the context of they've never even attempted it from space when there's 400 times better seeing. You can do the experiment 400 times easier from space, and they've never even tried it. What a fucking lie.
General relativity was more accurate than Newtonian gravity, writing that the deflection of light takes place in the neighborhood of the sun, and that it is of the amount demanded by Einstein's generalized theory of relativity. A lot of this stems from the
theory that
inability
he
to just
changed
detach
2
time.
years. So if they would have done the damn eclipse the 2 years earlier when they wanted to, Einstein would have been proven wrong, theoretically, because Einstein changed his equation in those 2 years. That's how bullshit this whole thing is.
The spatial axes. A distance in four-dimensional space-time can actually be a conserved quantity. So you really can't just rip that off and say, oh, space is falling the way that I have been. It's more like space is falling and maybe also time is passing at a different rate in that.
Yeah, maybe you have to have some sort of recognition of energy conservation. You can't make free momentum. So obviously, if stuff is gaining momentum from gravity, it has to be getting it from some source of momentum. There has to be some real source that it's getting the momentum from. Yeah, that would be called conservation, which you don't believe in, clearly.
That's falling. By rights, my diagram from earlier shouldn't have shown a shear of space-time, but actually a curvature of space-time, which also highlights that time passes at different rates near and far from massive bodies. But for relatively slow...
Bullshit, bullshit, bullshit. Time has to be the same because we're all in the same photonic field. We're in the same fucking universe with the same stuff flying around, going through us. And that's the damn clock.
Moving objects on Earth's surface, this effect is totally negligible, which is why, as a first-order approximation only, I like thinking of gravity this way, because it makes the whole inertial and gravitational mass thing make sense to me, and hopefully it also now helps to make sense of that for you. Now, it's really
Yeah, bullshit, propaganda nonsense.
dangerous to put out a video on the internet, and I don't want anyone to walk away from this video saying that Newtonian gravity is useless or bad or should be corrected, because it's an amazing tool that allows us to do a significant quantity.
So it's just still nonsense because Einstein didn't add anything but this silly time component that doesn't fix anything. It's the inverse square law. That's gravity. And the formula is the formula, and there's no evidence the formula doesn't work. There really isn't any evidence the formula doesn't work. And it's all based on assumptions. So all I have to do is to say, if I want to explain Mercury, all I have to do is move the center of the sun's mass. All I have to do is process the sun. So the idea that the sun is perfectly balanced in its motion is a non-starter because we know that every object isn't balanced. The Earth isn't a perfect sphere. Either is the sun. So the expectation that there could be no eccentricities in the sun's motion that would cause an effect that Mercury could feel but other planets couldn't feel because they're too far away is perfectly reasonable.
Be less math and get answers that are more accurate than we could ever possibly need for 99.99% of applications. Saying that it is incomplete is a lot better than saying that it's wrong. But of course, if you want to do something more complex...
Yeah, it's bullshit. It's not incomplete, and it wasn't an answer anyway. As Newton stated, he wasn't telling you what causes gravity, and that's the real argument, is what's the cause. And the obvious thing that I would argue that the cause has to have is energy, because it gives things motion.
Like synchronize clocks on passing satellites, or calculate the orbit of Mercury, or figure out why gravitational mass and inertial mass are the same thing, you're going to need the heavy stuff.
No, you don't. Bullshit, bullshit. Fuck you.
Thanks for watching, and I'll see you next time.
Yeah, fuck you. Fuck you, fuck you, fuck you. It's all bullshit. So that whole lie, the cheat that he did with that gravitational lensing image was just such bullshit. Again, they can never show it honestly, what they're actually detecting, and actually show what the actual experiments are. And the fact is, the Eddington experiment's the only one using images. And images are really important because, unlike scatter, you can't make an image out of scatter. So all the radio experiments are bullshit because they're just scatter experiments. Yeah, scatter goes everywhere. So it wouldn't matter where I go, I would say the light is bent. Okay, because it scatters to every location. But actual bending, okay, being bent by a force like gravity and bending the whole image, that's a completely different experiment. That's why the Eddington experiment needs to be redone. It's because it's a uniquely different experiment in the sense that it's actually bending an image. And they don't even acknowledge that. So that's how bullshit the whole thing is. So anyway, just more disappointing shit. You know, stated by humans on Earth. Yuck. Enough of a video, I guess.